Hello and welcome to ResearchPod. Thank you for listening and joining us today. Almost everything we know about our universe is based on observations of the light coming from space. These tell us about atoms, molecules, and material in the interstellar medium, and even in different types of stars. Some of this information dates from the early years of the universe. The discovery of the element sodium in the sun in 1858 using spectroscopic methods was of great general importance, as spectroscopy provided a way to investigate the composition of the sun from a great distance. Analysis of different wavelengths of the electromagnetic spectrum confirmed later that the sun also consists of material present on Earth. It took much longer to detect molecules in space. Some diatomic molecules were first observed in the interstellar medium before the Second World War, and larger molecules in the late 1960s. We might wonder how it's possible that the interstellar region, where temperatures are close to absolute zero, contains more than 300 different molecules and other material based on ice, solid methanol, and carbon dioxide, as well as on carbon and silicon. Some of these were formed by chemical reactions occurring despite the extreme conditions. We might ask why it matters that these molecules and material are there in the first place. The answer is that they are required for the formation of new stars. Our solar system has originated in the same way. In this episode, we're looking at research from an interdisciplinary network named COSY, led by Professors Maria Pilar de Lara Castells from Abenitsim Unit at the Institute of Fundamental Physics of the Spanish National Research Council, CSIC, and Cristina Puzzarini from the University of Bologna. COSY stands for Confined Molecular Systems, and the network's subtitle is From a New Generation of Materials to the Stars. Formed 2.5 years ago, COSY brings together 400 participants from 45 countries and is funded by the European Cooperation in Science and Technology (COST) agency. In particular, we're going to talk about a work group researching confined systems in astrochemistry, led by Professors Lauri Halonen from Helsinki University in Finland and Malgorzata Biczysko from Wroclaw University in Poland. The work group is engaged in laboratory and computational experiments on new molecules detected in the interstellar medium. It's exciting work. Using state-of-the-art equipment, researchers are observing the fingerprints of molecules, which are unstable species in atmospheric conditions. These unstable species are made in the laboratory by breaking stable molecules with heat or powerful laser beams. Professors Halonen, Biczysko, and their colleagues are taking a 3-tier approach to their astrochemical challenges. The first approach consists of the analysis of light coming from the interstellar medium and stars in the Milky Way and other galaxies. This branch of science belongs to spectroscopy. In the second one, laboratory spectroscopic experiments help to detect new molecules in the interstellar medium and stars. It is also possible to perform experiments that mimic reactions in space and determine reaction speeds. This is called chemical kinetics. The third approach comprises computational and theoretical work to interpret the results from the spectroscopic investigations. It's amazing what has already been achieved by spectroscopic observations of the light from the interstellar medium and stars. Spectroscopy allows us to observe the interaction between light and molecules or materials. Rather than being restricted to the light we see using our eyes, we can access information from longer wavelengths, including infrared and millimeter wave light, as well as shorter wavelengths, such as ultraviolet light. Large, powerful radio telescopes on the Earth enable us to detect millimeter waves, which are longer than infrared waves. This has made it feasible to identify many molecules freely rotating in the interstellar medium. Their concentrations can vary depending on the location in space. Work has been done, for example, on the notoriously poisonous carbon monoxide, the second most abundant molecule in our universe. Even though the concentrations of this species are locally very small, they can be detected using modern techniques. However, some molecules like the hydrogen molecule and carbon balls, tiny football-shaped molecules consisting of 60 carbon atoms, cannot be detected by observing molecular rotation. This occurs as these molecules possess a symmetrical distribution of positive and negative charges. While the carbon ball can absorb and emit infrared light, helping the detection, the hydrogen molecule is more demanding because it interacts only very weakly with infrared or millimeter light. There is a higher order effect which allows us to observe hydrogen molecules with infrared light, as they are the most abundant molecules in the universe. Earlier, scientists performed these types of experiments with spectrometers on Earth. However, the condition was far from optimum due to atmospheric weather vapor, which is a strong absorber in the infrared region. Nowadays, satellites with modern spectrometers and sensitive infrared detectors have produced beautiful infrared spectra of many molecules in space. Compared with infrared work, strong absorption and emission of light can also occur when changes of electronic motion in molecules takes place. An interesting example of this is the detection of the positively charged football molecule in the interstellar medium. Laboratory experiments are used to provide reference data to characterize molecules. This is needed to confirm their existence in space and to investigate the possible chemical reactions occurring in unusual conditions in the interstellar medium. Many of these reactions don't exist in our atmosphere. They're usually not even taught in university-level chemistry courses. It is very special that they take place at extremely low temperatures, close to absolute zero, about at minus 273 degrees Celsius. Typically, there is not enough energy to push the reactants together to form new products. This can be avoided by the reactions of a positively charged atom or molecule with a neutral molecule, where the interaction between these species helps to push the system into chemical reactions. Modern chemical laboratories can investigate such challenging reactions, which helps to understand the details of the matter in space. The research described above would be difficult without computational research. It applies both to the correct identification of molecules from the absorbed or emitted light and understanding chemical reactions. It could be a horrendously difficult issue because fundamental theory starts from many electrons and nuclei moving in molecular systems. Fortunately, the problem is not as bad as it might at first sound. Electrons are much lighter than nuclei and move significantly faster. This makes it possible to solve the electronic movement first and then the nuclear one. In fact, the solution of the electronic problem is needed to solve the nuclear one. If possible, the research team uses commercial computer programs for the electronic problem, but usually employs its own algorithms and computer programs for the nuclear problem in order to understand the light interaction with molecules. Quantum mechanics theory is used to understand both spectroscopy and chemical reactions. For spectroscopic observations, researchers need to know the details of the nuclear motions. Often, a simple application of the traditional nuclear motion theory leads to false conclusions or to time-consuming calculations. To make this workable, approximations are needed to concentrate on the essential aspects of the problem at hand. Part of the theory side of the team's research has concentrated on understanding details of chemical reactions. For chemical reactions to occur, it is necessary that the reactant molecules collide or at least get close to each other, including reactions both in the gas phase and on material surfaces. The theory and modeling of chemical reactions is demanding, not least when trying to explain observations. For example, how fast the reactions are and how they depend on external conditions such as temperature, even close to the absolute zero, or very hot environments, such as in the outer parts of stars. Professors Halonen and Biczysko say this is challenging, but doable. On the more philosophical aspects of COSY's work, professors argue that it is helping us to understand more about the fundamental nature of the universe. As they explain, human beings have always been interested in knowing why we're here. But how do the stars produce the light we see with our eyes? How were our solar system and particularly the Earth and Moon formed? And when and how were the first molecules, the molecules that were essential to cool down hot gaseous material after the Big Bang, formed? We're fortunate to live at a time when the world has become advanced enough to be able to answer some of these questions. This has required huge advances in experimental research, including building new computers and developing new mathematical tools and computer algorithms. More and more results will come out of COSY, but it still requires a lot of work and original ideas. As Professors Halonen and Biczysko say, it's very interesting research. Thanks very much for listening. You can find out more about the COSY Cost Action Network on the website cost-cosy.eu. Stay subscribed to ResearchPod for more of the latest science. See you again soon.